Hi, so welcome. So again, we're going to start with this with the equation 4, basically, all right? And let us use this. We said that we're going to look at that we will look at this equation for different values of alpha 1. So we've looked at positive, where we took the alpha 1 is equal to 1 without loss of generality, that we said. So now what we will do is we will set it to negative, and again we will put that to alpha 1 is equal to minus 1, right? And we will say let, okay, the thing that we have here, alpha 2 is equal to alpha 3, we will set that to be minus beta, right? Then what happens to equation 4? Right? If I do that, what happens to equation 4? So if I do that, let us come here. So this is essentially, well, the case 2, I think. Okay. So here, alpha 1 is equal to minus 1. Okay, alpha 1 is minus 1, then let, okay, alpha 2 equal to alpha 3 be equal to minus beta. Okay, then equation 4, that gives us what? That basically becomes f triple dash minus f of double dash, okay, minus beta 1 minus f dash square is equal to 0. Okay, and if I use say using, okay, again the power law, if I use the power law, so u infinity by v is equal to minus b zeta to the power m. Okay, if I use that, delta bar, okay, so it's the same procedure. Okay, I haven't sort of worked this out again to get the expression for delta bar. If you think you should do it, please do it. Okay, otherwise it would be just repeating the working out. So I've kind of done it once to drive home the point. I'm not going to repeat it. Please feel free to practice this if you need. Okay, so okay, so delta bar then comes out to be, okay, comes out to be 2 by b 1 plus m, okay, zeta to the power 1 minus m by 2. Okay. So now again, so here what kind of stuff are we going to see? So all we are doing here is assigning different values to alpha 1, alpha 2, alpha 3 and seeing what we get, right? So here again, okay, the outside outside the boundary layer, okay, is inviscid flow, right? Inviscid flow, and yeah, I mean, the kind of flow that we were sort of looking at. So when we define the first case, that it's basically if you had a wedge like this, right, we said we'll have a wedge like that, and we had flow impinging this way, right, and you had flow moving this way, right. In this case, however, the sign of the velocity is changed. If you see this, okay, sign of the velocity is changed. So I would have velocity in this direction. So outside the boundary layer is inviscid flow, right? Past wedge. Basically what I'm saying is what this means, right? What this means. Past wedge, okay, with the, okay, I'm sorry about that. Okay, okay, with the sign of the velocity changed. Okay, so outside the boundary layer is inviscid flow, past wedge with the sign of the velocity changed. Okay, so again here I will give you the particular cases what will arise depending on the kind of values of m and beta that we are going to use. So number one, okay, is walls of moving plates, okay, walls of moving plates. So m is equal to minus half. So if you have m equal to minus half, it basically you should be able to study flow of walls of moving plates. Okay. Then you got free jets. Okay, you got free jets for which m is equal to minus 2 by 3, right? So this is the case where we said that alpha is going to be negative, right? Alpha is going to be negative. So we see that m seems to be negative as well, right? So we're taking all negative values. So free jets, okay, then we got wall jets, right, where m is equal to minus 3 by 4. Okay, and well, flow through nozzles with contoured walls also. Okay, and okay, so now if you see m is, if you see m, okay, less than 0, okay, if you see m less than 0, okay, what that essentially means is that accelerated flows, right, if m is negative, right, if m is negative, so then what we kind of understand is that it is basically accelerated flows. Okay, so of course these are physically important, right, whether it's flow past, you know, something like this, flow past airfoils and flow past cylinders, right. So accelerated flows, right, are physically important. Okay, and we'll kind of you know, as we learn slowly as we move on, you know, towards the end, I think, of these set of lectures, we will also talk about separation. So I think we'll kind of touch upon that, you know, regarding accelerated flows and things like that, because are physically important. What happens if, you know, flows are not accelerated, so which is like for m positive. Okay, so we'll kind of talk about that. So I will just sort of write it here. It's like a note. Okay, it's okay if you know, find it a little confusing, but hopefully we'll touch back on this, you know, towards the end of the lectures. Okay, so for m positive, okay, that is decelerated flows. That is decelerated flows. backflow occurs. I guess what we're trying to say here is that, accelerated flows keep the direction of flow. It allows the flow to keep going. Let's put it that way. Decelerated flows, it kind of pulls back the flow, okay? And backflow, you're probably even familiar where we talk about backflow, and it's really when flow separates, okay? So, so these are flows which are important, okay? If we can, keep flows from not separating, it's good for us, okay? Fine, so that's that. So if you have alpha, negative, this is what we come up with, okay? So going to the next part, where it is alpha 1 is basically, so this is case 3, right, where we said that alpha 1 is equal to 0. So if alpha 1 is equal to 0, okay, what we're talking about, and then alpha 2 is equal to alpha 3, okay, alpha 1 is equal to, okay, so alpha 1 is alpha 1 is 0, and alpha 2 is equal to alpha 3 is equal to 1, 1, right? This actually boils down to convergent channel, right, or sink flow, right? So you could have convergent like channel, and sink flow is basically flow moving into a sink, something like that. Okay, so so that's that basically. So you get the idea that if I were to, right, do this, then how will we? So if we were to take different values of m and beta and things like that, we should be able to basically, look at various types of flows. So in the sense that here again, like I said, it's upon you that you need to choose, judiciously, and you need to choose. You need to choose the kind of the numerical values in order to study the physical phenomena that you're trying to. So of course one needs a little bit of experience with that. So let's see a couple of examples of that. So what I will term this part is, how do I choose a similar solution, right? What do I how do I exactly go about this? Okay, so what I'm going to term this part is choosing similar solutions. Okay, so what let us use the power law. Okay, so the way we will use the power law is this. Okay, now let us choose b, okay, the constant b, in order to set the reference velocity. Okay, and so let, okay, b be equal to 1. So we can just say b is equal to 1, right? Then for zeta is equal to 1, right? That is, zeta is equal to x by L equal to 1, right? Or x is equal to L, right? So here b is equal to 1, okay, and zeta is equal to 1, which means zeta is equal to x by L, which is equal to 1, or x is equal to L, right? So u infinity is equal to v, right? So if we do this, right, so what is that? What does this kind of mean? So basically, we're taking a reference velocity, right? So this is equal to the outer inviscid flow. That is all. So, what this means is that the reference velocity, right, is equal to the velocity of the outer inviscid flow. The outer inviscid, right, and of course, the origin of the coordinates can be chosen arbitrarily. I mean, zeta may not have to be 0 or 1 or whatever. So, let us say it is zeta naught and eta naught. Okay, let the origin be that. So, we can choose origin of coordinates is arbitrary. Okay. Therefore, zeta is equal to zeta minus zeta naught, right. So, therefore, so the inference here is that if the outer inviscid velocity, right. So, if the outer inviscid, so of course, here we are basically assuming that the inviscid flow outside obeys the power law. So, if the outer inviscid velocity obeys the power law, okay, now such similar flows, yeah, so we can actually devise means of using that velocity, and we can assume similar flows, okay, and that kind of potential flows occurs across wedge-shaped bodies, wedge-shaped bodies. This is a wedge, okay. They flow past what kind of, when I say that, what does that even mean, okay. Let me just give an example of that. So, wedge-shaped bodies, and therefore, these are called wedge flows. Okay. So, let me just write that here. So, this final inference, okay, inference is that if the outer inviscid flow, okay, velocity obeys the power law, okay, such, I mean, such similar solutions are possible. Are possible, okay, and such similar flows are possible, and they occur past wedge shaped bodies and hence called wedge flows, right. It is called right. So, let me just kind of briefly elaborate on that a little bit. What exactly do we mean by wedge flows, right. So, what exactly do we mean by wedge flows? Okay. So, okay. So, now for example, something like this. Okay. Now, these are the type of corners flows will encounter. Okay, so these are the type of corners flows will encounter. So you have a flow, right? So it comes in, right? It's a free stream which comes like that. Then what does it do? It turns, right? It turns. It turns, okay? And right? So this is mod of beta pi by 2, right? Mod of beta pi by 2. So this is actually a corner flow. So let me write that down. This is actually a corner flow, right? Here, M, right, is between so it's negative, okay, and it's less than minus 0.5, and beta lies between, again, minus 2. So that will automatically come, right, if you are looking at M. So if you use, if you restrict your solution to these, you should be able to find the solution for corner flow, okay. Then again, the wedge flow that we've been talking about so far. So this is a wedge flow, okay. So we've got this here. Right, and we have, again, we have flow coming in, right, and it will go like that, and it will go like that. Okay, so, well, actually, this should be a little more rounded, and this should be a little more. So, for example, let's do this, okay. This is the stuff, and then, right, and also this one, and well, these should be parallel actually. Please bear with me. So these will be kind of parallel to each other, okay. And here, okay, so this stuff beta pi by 2, right, beta pi by 2, and this here, this is basically wedge flow, right, this is wedge flow, and M here is positive, right, it has large value, and beta, this, right, and yeah, so we know that, right. So that now M is of course beta by 2 minus beta, right, and the cone, well, wedge actually. So beta pi by 2 is half wedge angle. So this what this is called is half wedge angle. So this is the wedge angle, this whole thing, right. So that is the, say, wedge angle, say theta. So this is half of that. So it's called half wedge angle. Okay, so that's so this is basically okay. So now so far we've sort of talked about this, right. So we've been talking about velocity a lot, right. I mean, in fact, we've just talked about just velocity. Now, what we said is that in the velocity, profile, similar solutions exist, right? If the outer flow follows a power law, right? If it follows a power law, now the wall temperature also follows, a power law, and hence, similar solutions exist. Okay, if you're going to look at that, so wall temperature also will follow a power law, and similar solutions exist. So if I were to do that, okay, so here what we will do is kind of use our definition of the velocity and the reference velocity and the outer velocity as a power law, and use that in the energy equation, right? If I use that in an energy equation, so what shall we get? What does that boil down to? So that's what we're going to talk about. So let me sort of, at least let us begin that, a little bit. Probably we'll need some more time to complete that, but let's say, so we will use this trial solution again. So we will use zeta is equal to x by L, okay, eta is y by L under root of Re by delta bar zeta, right? Then of course we have, this is so u x of y, okay, is equal to un zeta f dash eta, right? Then minus v xy is equal to 1 by under root of Re, okay, f of eta d d zeta of un delta bar minus un d delta bar d zeta eta f dash. Okay. Now, if I use in the momentum equation and the energy equation. Since I haven't written the energy equation, let me write that down. Okay. I'm not going to write out the x momentum equation, that you know already. So the energy equation, okay, is essentially u del t del x, okay, plus v del t del y is equal to alpha del 2t del y2, and this alpha is equal to lambda by rho into Cp. Okay, so this is my energy equation, and if I were to use, so if I use this definition here, right? If I were to use the definition here, using alpha 1, alpha 2, alpha 3, etc. in the momentum equation, this is what we will get from, I'm just repeating this here, what we just got earlier, right? This is basically equation 4 plus alpha 1 f of f double dash plus alpha 2 minus alpha 3 f dash of square is equal to 0. So this is earlier derived. Right, this is something we've done earlier. Now here, so if I do this again for the energy equation, what I actually get is, theta double dot plus Prandtl number alpha 1 f of theta dash minus alpha 4 f dash of theta is equal to 0, right? So this is, let me call this as, so this is the equation that we get okay, and let's call this as 11. Okay. Now, alpha 1, alpha 2 and alpha 3 are as we have described, earlier, right, and alpha 4, right. So, alpha 4 is and un theta delta bar square, okay, phi theta. Okay, and boundary conditions, okay, boundary conditions at eta is equal to 0, theta is equal to 1, right, eta tends to infinity, theta is equal to 0. So, basically theta goes from 1 to yeah, so theta at is 1 and at the edge of the boundary or far away from the boundary layer theta is 0. Okay. So, I will come back in the next module and elaborate a little bit on this, okay, to I think some things will need to be explained a little bit. I will do that in the next class. Okay. So, let us stop here. Okay. So, we've sort of compartmentalized a lot of the solutions are large, as you can see, that it is the possibilities are several, which is a good thing, right, which is a good thing. So, we started out where we said that the outer flow is not 0, right. So, we were going to do the solution that way. So, outer flow is not 0 and hence we had to find out that what are the possibilities there, and we'll do the next one where we will have the outer flow as 0. So, what kind of I think it must have crossed your mind that what does that even mean, that you don't have an outer flow and you have a boundary layer, right. So, we'll just kind of discuss that in the next class, and well, we haven't talked about the thermal boundary layer. We will, okay, we will, but here just we will kind of see numerically if I apply these expressions to the energy equation, what kind of stuff we get and what are we talking about. So, I think we will do that a little bit, right, to get us started, and slowly when we move on to the thermal boundary layer, then of course formally we'll talk about it. Okay. So, I will stop here and I will meet you in the next lectures. So, thank you.